So to solve a DC current circuit, we have to go through and identify the 4 properties at each of the components in that circuit. So we need to find the voltage, either the voltage produced or the voltage consumed at each component, or the current that comes out of the battery or passes through each resistor. We need to find the resistance total experienced by the battery, and we need to find the power consumption of each piece in addition to the power output of our electron source. So to start off, this thing here, DC circuits, the D stands for direct and the C stands for current. So direct current means that electrons are leaving the battery, traveling through the circuit and coming back in, so they move in one direction through the circuit as it goes. The other option is an AC circuit, A for alternating, so it's alternating current. In that sort of electricity, the electrons are pushed forwards for a moment and then they're pulled back, and then pushed forward and pulled back, so that the wire, like, it quivers with electricity instead of having flow through it. So direct current is provided by batteries, basically. There are machines, like every machine that you work with actually runs on direct current, so you need a little piece in your circuit board in order to turn alternating current from your wall into direct current so that the electronics behave themselves properly. But alternating current is made basically by turbines and generators. So if you have a nuclear plant producing electricity, or a hydroelectric dam or a windmill, whatever's turning, on this half of the turn that machine is pushing the electrons out, and on this half of the turn it's pulling them back. So as that thing spins, with each rotation of the turbine, it pushes the electrons out and pulls them back in a nice wave kind of way. So we're going to stick with direct current because it's just pretty straightforward. So there's a lot of information to gather here, right? There's 4 features of 4 different components. That's 16 different numbers I'm going to have to cook up from somewhere. So I found in the past that it's wise to make a chart just to gather the information. So the things I need to be able to solve then are the voltage, the current, the resistance, and the power consumption. And in this particular circuit, there are 3 resistors and a battery. So I'm going to put the battery here, down at the bottom. So I can go through and I can gather a few of these pieces of information just from the diagram, right? I have this electron source here, that's the symbol for a battery, running at 12 volts. So I've connected a 12 volt battery in series with a 13 ohm resistor, a 6 ohm resistor, and a 5 ohm resistor. And now we can't rest until this entire chart is filled out. So you're going to want steps, but there aren't steps. You have to think your way through this. You have to look at the information that's been provided and then see if there's anything at all you can calculate. And then once you calculate that, you put it in the chart and then reassess. Now that you have a new number, is there something else that you can calculate? This is very much like the kinematics problems, right? If I work through this information, I get a number, then I can use that number to find something else. So if I look at this little thing here, I see 3 resistors in series, and from the last section I know that if there's 13, 6, and 5 all in series, then I would add those just normally to get the total resistance experienced by the battery. So 13 and 6 would be 19. 19 plus 5 would be 24. So the battery has to beat 24 ohms of resistance. I can just park that in my chart. So now that I have a number there, I'm going to see if there's anything else I can calculate. Well, the equations I'm using are power is current times voltage, and voltage is current times resistance. So if I knew the voltage and the current, I could calculate the power. But I don't have the current, so I can't do that. If I had the current and the resistance, I could calculate the voltage. Well, I already have the voltage and I have the resistance, but I don't have the current. So I could use this to solve current then. So I'm gonna do that. I'm gonna take my 12 volts and my unknown current and the total resistance experienced by the battery, which is 24. I'm gonna divide both sides by 24. And that ends up being 0.5. Alright, so I can put that in here then, 0.5 amps. Alright, now here's where you have to do a little bit of thinking. If half an amp is coming out of this battery, then that half amp goes through this resistor. And all of it has to. There's no branch for it to split. So if half comes out of here, half must go through this. And then half must go through this, and then half must go through that. So the current everywhere on here has to match, because there's only one pathway. If I've calculated it at being 0.5 amps, then I can just transcribe this all the way up through my chart. And if you look, now that I've done that, I have currents and resistances for all three of these resistors, which means I can use Ohm's law in order to calculate the voltage. Let me get this out of the way. Alright, so if it's current times resistance, 0.5 times 13 would be 6.5 volts. And then 0.5 times 6 would be 3 of those volts. And 0.5 times 5 would be 2.5 of those volts. Now, in a nice conservation of energy kind of way, this battery was pumping out 12 volts. That's 12 joules per coulomb. These things have to absorb that energy. So whatever energy has been produced, each pathway has to add up to 12. And since there's only one pathway, it's not that complicated. 2.5 plus 3 is 5.5, plus 6 is 11.5, plus a half would be 12. So I can double check this, making sure that this all adds up to the right number. To get my power, I just need to take the current times the voltage. So 0.5 times 6.5 would be 3.25 watts. 3 times 0.5 would be 1.5 watts. 2.5 times 5 would be 1.25 watts. And 12 times 0.5 would be 6 watts. So this battery is pumping out 6 watts worth of power, and these components are absorbing, well, 3.25 and 1.25. That's 4.5 plus 1 is 5.5 plus a half is 6. Notice that this column also matched the power output of the battery. So that's encouraging. Oh, we're done. So just accidentally, you ended up filling up that chart, and now you know all 4 variables, all 4 properties for all 4 components as soon as that chart is filled. So this circuit then is solved. So I'm going to erase this one, and then we're going to walk through one that has parallel components. All right. So I have a 30 ohm resistor and a 60 ohm resistor wired in parallel, and they are connected to a 21 volt battery. So if I put myself, make myself a chart here, then the four properties are voltage, current, resistance, and power. And I only have 3 components in this particular circuit. 2 resistors and a battery. I'm going to put the battery at the bottom. Alright, so if I go through, I can fill in some of these numbers. It's a 21 volt battery, and one resistor is 30 ohms, and the other is 60. Now you may be tempted to write 90 here based on the last example, but that wouldn't work. These are not they're not arranged in series. They're arranged in parallel. So you have to think about how to add resistors in parallel. You have to remember that you use this fancy thing. So for this segment then, 1 over the total resistance of this thing would be 1 over 30 plus 1 over 60. Now that's 2 60ths. So that's 3 over 60, and then flip both sides. I get 60 over 3, which is 20 ohms. All right, lovely. So the number that goes here then is the resistance, the total resistance experienced by the circuit. It's not just the sum of the resistors, it's how they behave. I'm going to park my 20 in here. And then I can get rid of this because I don't need it. But you'll notice that I ended up with the same situation as I did in the last example. I know the resistance, the total resistance of the circuit now, and I know the voltage of the battery. So once I have those two things, I can calculate the current using Ohm's law. So my current there, voltage is 21. Current I don't know. Resistance total is 20. So I end up with 21 over 20 equals I. And I'm pretty sure that's 1.05. And I'm going to grab a calculator to check. 21 divided by 20 is 1.05. Perfect. So I have 1.05 amps of current flowing through that circuit. And I'm going to write that in a different color. 1.05. Excellent. Okay. In the last example, because it was all series, I took this current and I just copied and pasted it into these two slots. But that, again, isn't going to work for this example. If 1.05 amps of current come out of this battery, they can't all go down through this resistor. If they all did, there'd be no current left to go through that one. So this is one of the Kirchhoff's laws, right? That when current splits, it has to add up to the total. So because there's a split here, these currents aren't going to match. But what you can use instead is that resistors don't have brains, right? They don't. This resistor doesn't know that this one exists. So if you, well, if I cover it, I can't see it. I bet you can see it still though. All this resistor sees is a 21 volt battery attached to it. So it's going to take all 21 volts of this voltage because it's the only resistor in that path. Same thing's going to happen here. Along this pathway, there is only this resistor, so it must bear the full voltage of that battery. So in a parallel structure, instead of copying and pasting the current up, I get to copy and paste the voltage up through the system. So because it's in parallel, this 30 ohm resistor is going to experience all 21 volts, as will this. All right. So using Ohm's law, just like this, I'm going to be able to use the voltage and the resistance to calculate the current through each part. And before I do, I'm going to get some current through here, through this 30. I'm going to get some current through that 60. And when I'm done, I should be able to add them together to get 1.05 so that everything is accounted for. So let's just do that and then make sure it works. So I don't need this anymore. Get it off my face. There we go. So I need to do voltage divided by resistance to get current. So 21 divided by 30 gives me 0.7. And 21 divided by 60 gives me 21 divided by 60 is 0.35. And that's really encouraging because I have 0.7 and 0.35, and those two things add up to 1.05 amps of current. So 1.05 amps come out of this battery, and 0.7 of them choose this branch, and 0.35 of them choose that branch. And that should make sense. There's more current going through the lower resistor. In fact, there's twice as much current going through this resistor because this resistance is twice what that is, right? Like, it's all proportional. So you can use these little number facts to try and check your work to make sure you've done things correctly. Last column I need is the power. I get power from current times voltage, so that's these two numbers multiplied. So 21 times 0.7 gives me 14.7 watts. Let's see, let's put this in pink. 21 times 0.35 is 7.35 watts. And 21 times 1.05 is 22.05 watts. And 14 and 7 is 21. 0.7 and 0.35 is 1.05, plus that extra 1 would be 22.05. Perfect. All right, so this circuit is solved. We're going to do two more examples. One will be a pretty straightforward series and parallel mixed circuit, and then we'll do one that's a touch more complicated, and then we'll just go to the practice problems. All right, so looking at this particular circuit, I have 4 components, 1, 2, 3 resistors, and 1 battery. So I'm going to build myself a chart. Voltage, current, resistance, and power for 1, 2, 3 resistors, and 1 battery. So going through and collecting the gathered information, I have these 2 resistors in parallel, and I have this one in series, and I have a 15-volt battery. So you might want to make a little note to yourself that these 2 things are wired in parallel. Because we're going to need that fact later. So that's a big mess there, but you are very proficient in collapsing parallel and series circuits or resistors now. So we're going to get this total resistance by working our magic from yesterday onto this particular set. So first off, I see this and this wired in parallel. So I'm going to figure out what they're worth together. So 1 over 18 plus 1 over 24. Well, that's 3 6s. This is 4 6s. So this is missing a factor of 4. And this is missing a factor of 3. For a total of 7 over 3 times 4 is 12. 12 times 6 is 72. So this thing here then, don't forget to flip it, would be 72 over 7, which is approximately 10.286. There's more to that, but I'm going to clip it off at 3 decimal points. If you feel like a challenge, you could just use this fraction. Park the fraction into your chart and then go from there. That's not required, but if you want a little to stretch your legs with your fraction skills, it would be a good exercise. So this thing here was worth 10.286. I'm just going to write that in my diagram there. So if this structure is worth 10.286 ohms, and it's wired in series with 6 ohms, then I should get the total resistance by adding this to this, which would end up giving me a total of 16.286 ohms. All right, let me get rid of this mess. And you see, though, again, that we've got the total resistance for the circuit and the total voltage for the circuit, which is going to allow us to get our currents. And once we have our currents, then we can just sort of start filling things into the chart. So by Ohm's law up here, if I have 15 for my voltage and 16.286 for my resistance, I could do this divided by that, and it would give me my current. So 15 divided by 16.286 is 0.921. All right. So there's 0.921 amps of current flowing out of that battery because it's a 15 volt battery and it has this much resistance in total fighting back against it. So I know that much is going to flow. I don't know how it flows around these two objects because there's a branch. Some of it goes that way, some of it goes that way. So I can't put this number into either of these slots. But once it goes through that structure, it all comes back together and every bit of current must flow through that 6 ohm resistor. So this current all passes through this component. So I can jot that in. Now, if I have a current and a resistance, right, Ohm's law lets me calculate the voltage. So I'm going to do that. Current times resistance, 0.921 times 6 is 5.526 volts. Extend this box here. All right. So 5.526 of these 15 volts are going to get dropped on that particular resistor. Now the trick about a DC circuit is that every pathway has to consume all 15 volts. So it all has to be accounted for. So on this particular branch, down and up and through the 18, this resistor has to bear whatever's left over, which is around 9.5. On this branch, this one also has to bear whatever's left over. So if I could figure out how much voltage hasn't been accounted for yet and assign it to either this resistor or this resistor, I'm going to have two more numbers in my chart. So there were 15 volts to start with, and I've already accounted for 5.526 of them. So if I subtract that from the total, I'd end up with 9.474 volts. And those 9.474 volts are either absorbed here or they're absorbed here. Well, once I have voltages and resistances, I can calculate currents. So I'm going to take my voltage and I'm going to divide it by my resistance. So 9.474 divided by 18 gives me 0.526 amps. And in this slot, I'm going to have the 9.474 divided by 24 ohms gives me 0.935. 0.395. So just to fact check my work, these currents are different because there's a branch there, but if I add them together, they should give me the total current flowing through the circuit. So if you just check that, 0.395 plus 0.526 ends up giving me, these two numbers together give me 0.921. So that's good. Everything is accounted for, everything is consistent. Last thing to finish are my power ratings for all four components. Power is, of course, current times the voltage. So I need a bigger box here again. 9.474 volts multiplied by 0.526 amps gives me 4.983 watts. And in this row, the 9.474 volts multiplied by 0.395 amps is 3.742 watts. The 5.526 volts multiplied by 0.921 amps is 5.089 watts. And my 15 volt battery pumping out 0.921 amps of current is operating at 13.815 watts. And again, just as a final fact check, whatever wattage is produced must be consumed. So these three numbers added together better give me 13.815. So 4 and 3 is 7, 7 and 5 is 12. 12 is almost this. 0.9 and 0.7 would be 1.6 plus a little bit. I bet that does add up. So let's try 4.983 plus 3.742 is 8.725 plus 5.089 gives me 13.814. So with a rounding error, I'm getting this number back. So I've solved this circuit. It was more complicated. I had to think about what the total resistance was. And then I had to think about which things bear the full current, which things bear parts of current, which things bear voltage on their own, or which voltages can be shared across two components. But the flavor of the question is the same. So I'm going to try one that's a touch more complicated, and then we'll be off to the practice problems. Alright, so that's a monster there. I have 1, 2, 3, 4, 5, 6, 7 components, 6 of which are resistors, 1 is a battery. So I'm going to have to make myself a grande chart for this one. Volts, current, resistance, power. For 1 resistor, 2 resistors, 3 resistors, 4, 5, 1, 2, 3, 4, 5, 6 resistors, and a battery. Alright, so I can go through and I can gather the information that was given to me. The battery is 24 volts, and I have a 7 ohm and I have an 8 ohm that are in a series component. And then I have these 3 things, a 6, a 9, and a 5, that are all wired in series with each other, but they happen to be in parallel with a 30. So I'm going to make a little box around these ones here, the 6, the 9, and the 5, because they have something in common. That is a horrible screaming sound. And I'm going to draw another box around this box and the 30 to remind myself that they are wired together in parallel. Alright, and then I'm going to start doing some work on this. So this, and this could basically be considered a single resistor with resistance of 5 plus 6 is 11 plus 9 is 20. So this all the way around here, that's worth 20 ohms. And then this little structure here, this is going to end up being parallel, right? It's a 30 in parallel with this branch that's worth 20. So my total resistance for this little structure would be 1 over 30 plus 1 over 20. That would be 2/60ths and 3/60ths for a total of 5/60ths. And you have to flip it. So that's 1 over the R total. So I end up with the total for this little structure here as 60 over 5, which is 12. So this entire structure then is worth 12 ohms altogether. A 7 and an 8 wired in series with a bunch of crap that's worth about 12 ohms adds up to 8 and 12 is 20, 20 plus 7 is 27 ohms in total, and then that's my resistance for the battery. Alright, so total resistance that this battery is facing from all of these resistors, what did I just say it was? 27? 12 plus 8 is 20 plus 7 is 27. Yes, 27 ohms. Alright. So, you see the pattern that's happening here. You get the total resistance of the circuit, no matter how complicated it is, and then given the voltage of the battery, you can get the current that will flow. So, from a voltage and a resistance, with my Ohm's law, I need to take my voltage divided by resistance, and that will give me my current. So 24 divided by 27 is 8/9, 0.889. So 0.889 amps worth of current are going to flow through that battery. They come out of there and they immediately go through this 8 ohm resistor. So I can find the 8 ohm resistor in my chart, and I can assign all of that current to flow through it. Then some magic happens here, right? The current splits. So I don't know how much goes through this, and I don't know how much goes through this branch. But I do know it all comes back together before passing through this 7 ohm resistor. So this 7 ohms, which is in this row, is also going to bear the full current. All right, good. Now, I've got a few rows. I have 2 here where I have a current and a resistance. So if I have a current and a resistance, I can calculate voltage with Ohm's law. So I'm going to do that. Got my .889 times 7 gives me 6.222. And if I take my .889 times 8, I get 7.1111. All right, lovely. So this is what's going through this component and this component. So I have 6.222 and 7.111 of my 24 volts accounted for. So if I look in here, if I ignore this bottom branch for a minute, I have a pathway that goes through that 8, through the 30, through the 7. So any voltage that is not accounted for in either this component or this component must be found in this one. So if I take my 24 and take out the voltages that are accounted for, let's see what I get there. 24 minus 6.222 minus 7.111 leaves me with 10.667. So that 10.667 worth of voltage must be accounted for in this 30 ohm resistor. That's here, so in it goes. All right. Well, I have a voltage and a resistance now, so I can use Ohm's law to get current by taking the voltage divided by the resistance. So if I take that number there, divide it by 30, I get 0.3555. We'll round that to 0.3556. All right. Well, this is one of the branches, right? 0.889 amps comes down here, and then 0.356 of those amps peel off in this direction. So whatever's left over must be what the current is through this bottom branch. So if I could take that out of this, I could put it here. Let's try that. So 0.889 minus 0.356 is 0.533. So at this branch, 0.356 of the amps go this way and 0.533 amps go that way. Well, these 0.533 amps must then pass through the 9 ohm resistor and this 6 ohm resistor before rejoining the main current to have 0.889 pass through and then back into the battery. All right, so I have 0.533 and, in all of these categories, and I have a current and a resistance, so I just need to calculate the voltage with Ohm's law. So give that a try. 0.533 times 5 is 2.665. And then 0.533 multiplied by 9 gives me 4.797. And then 0.533 multiplied by 6 gives me 3.198. So that was a lot of work. I'm going to try and fact check these here. So I have this number, and this number in a series circuit. So these three things, if I add them together, I'm just going to see what I get. 3.198 plus 4.797 plus 2.665 gives me 10.66. Well, look at that. If this branch of the parallel structure is experiencing 10.66 volts, then this branch must also be experiencing that. That happened in both of the examples before that had parallel structures. Right? Once you had a split, whatever voltage was happening here was applied to both branches. So on this branch, one resistor bore all of it. On this branch, that 10.67 was shared over three components, but it's all accounted for. These two currents, 0.356 and 0.533, that's where the branch was, add up to the total current that was going through. And these two things, plus either this branch or this branch, add up to 24. So it's all nice and internally consistent. The only thing left for me to do is to calculate my power values. So I'll go through, get that done. Power is current times voltage, so 0.889 multiplied by 6.222 is 5.531. .111 volts multiplied by 0.8889. Oop, that's too many. That's too many. There we go. Is 6.322. .198 multiplied by 0.533 gives me 1.705. 4.797 times 0.533 gives me 2.557. 2.665 times 0.533 gives me 1.420. 10.667 times 0.356 gives me 0.593. That's not right. 10.667 times 0.356 gives me 3.797. And my 24 volt battery pumping out 0.889 amps of current is operating at 21.336 watts. Now, this is the killer fact check column, because you can't have more power consumed in these numbers than is produced by the electron source. So if I were to add all these things up, they better add up to 21.336. So let me give it a try. 5.531 plus 6.322 gives me 11.8-ish. Plus this one gives me 13.5. Plus this one gives me 16.1. Plus this one gives me 17.5. Plus this one gives me 21.332. So I did a whole bunch of rounding here, but I ended up getting 21.332 as my total powers I had 21.336 as my total power produced. So my rounding error is only accounted for 2/1000ths of a watt. I think we can tolerate 2 milliwatts as an error on our calculations here. But they nicely added up to the power that was produced by the battery. So there's a lot of options here for fact checking, and then this column's the real killer at the end. If these don't add up to this, then you've made some sort of error somewhere else in the chart. But really the trick to this was getting this number at first, right? This total resistance of the battery. That's the place you always have to start, which is why we spent so much time in the last section hacking through that and making sure you could do it. So if you start with that with each problem, collapse the whole monster pile of resistors into a single total resistance, and then get your current, and then you try and puzzle